In this video, we analyze the operations of the 510 Spadina Streetcar line in Toronto and assess various measures to improve its performance. This video will be organized as follows. First, we begin with a general description of the route and the conditions in which the route operated during the time of study. Next, we examine the problems and deficiencies in performance and propose various measures to improve operations. The metric to assess effectiveness is lost time, as explained later in this video. Thirdly, we explain the methodology of study, followed by a detailed discussion of the results under the different measures proposed. Lastly, we finish by recapping the most interesting findings and present the recommended measures to be implemented. Please feel free to skip to any chapter by clicking on the times in the video description below. The 510 Spadina line is a streetcar line that operates along Spadina Avenue in downtown Toronto. The current route operates on a 5-kilometer route from Union Subway Station to Spadina Subway Station, connecting with 6 other surface transit routes and serving a total of 17 stops every 250 meters. Today, the Spadina Streetcar carries over 40,000 riders per day, ranking it the 6th busiest route out of 150 surface routes in Toronto. The Spadina Streetcar runs on a Type B right-of-way, in which streetcars operate in physically separated transit lanes at street level. To allow for left turn lanes, all major stops are located far side after the intersection. Our study was based on operations as they were in March of 2014. At the time of study, the streetcar line ran along Spadina Avenue between Bloor Street West and King Street West, creating a 2.5-kilometer long route each way. At the southern end of the line, near King Street West, streetcars ran in mixed traffic for about 400 meters before re-entering the dedicated transit lanes in the opposite northbound direction. At the southern terminal at King and Charlotte Streets, streetcars would continue through the loop onto King Street without waiting or taking any breaks or terminal time. In order to continue their trip in the northbound direction via King Street West, streetcars would wait for an adequate gap in traffic before forcing their way onto King Street. In this study, the line was therefore considered as a one-direction loop, with the only terminus being at Spadina Subway Station. A total of 18 uncoupled Canadian light rail vehicles were used, scheduled to run every 2 minutes. Introduced in 1978, the Canadian Light Rail Vehicle, or CLRV for short, is a high-floor streetcar with a length of 15 meters and a capacity of 74 sitting and standing passengers. Each streetcar is equipped with 2 doorways. The front door, where the operator sits and collects fares, can accommodate 1 channel of passenger flow. The back door, located 7 meters from the front, can accommodate 2 channels of passenger flow. Despite the exclusive transit lanes, the 510 Spadina line is one of the slowest surface routes in the city, with an average operating speed of 12 kilometers per hour. Ride check and speed and delay surveys were performed 3 times over March of 2014, during the evening rush hour. Our analysis of the base situation reveals the following sources of delay. As much as 17% of their trip time is lost due to red lights. Another 25% is lost servicing transit stops. 14% is lost due to mixed traffic congestion. 7% is lost due to the bunching of streetcars. And 27% is lost in streetcar queues that form at the King and Charlotte Streets bottleneck. There were a number of factors that contributed to these delays. Firstly, as the Spadina streetcar operates at street level, it must adhere to the same traffic control system at all intersections. Of the 12 signalized intersections, 6 do not have any form of transit signal priority. Furthermore, the current far-side arrangement at major stops causes streetcars to double stop, once before the intersection for red lights and again after the intersection to service the streetcar stop. Secondly, at 2-minute headways, the Spadina Streetcar is one of the most frequent surface routes. Coupled with random passenger demand and influences from other traffic and signals, this high frequency inevitably leads to the bunching of streetcars. Thirdly, at the time of study, passengers would pay and board via the front doors and alight via the rear doors exclusively. This loading regime is often considered as inefficient for lines with high boarding demand. For stops at which many passengers want to board, single-door loading would cause a long queue of boarding passengers to form at the front door. Fourthly, at King and Charlotte Streets, streetcars are forced to wait for a gap before executing the right turn. Coupled with heavy traffic conditions westbound on King Street and the high frequency of streetcars, this creates a bottleneck and conditions for long queues, occupying all of Charlotte Street and even spilling back onto Adelaide Street West. Lastly, these delays are further exacerbated by the TTC's stop and proceed policy, a policy that requires streetcars to stop at every face-pointing switch to observe that the switch is set correctly, and proceed with caution over any special track work. The Spadina Streetcar route passes over 14 face-pointing switches, which causes an average of 1.5 minutes of lost time alone. In light of these sources of delays, we test the effectiveness of common speed increasing measures often employed by transit designers and proposed by members of the public. The measures we study are all-door loading with CLRVs, new longer low-floor vehicles with all-door loading at reduced frequency, stop consolidation, and finally, the repeal of the stop and proceed policy for face-pointing switches. To assess the effectiveness of each measure, we ask the following question. What is the impact of different proposed solutions on round-trip time, also known as cycle time? And where are these time savings being realized? Let's look at each measure in detail. In the all-door loading scenario, passengers may board or alight through any of the doors of the vehicle. The number of available boarding channels is increased from 1 to 3, and the number of available alighting channels is increased from 2 to 3. The scheduled headway is maintained at every 2 minutes. In this scenario, new low-floor streetcars, also known as low-floor light rail vehicles, are used. At 30 meters long, the low-floor LRVs are twice as long as the CLRVs, with a total capacity of 130 passengers. All-door loading must be used. Each vehicle is equipped with 2 single-channel doorways and 2 double-channel doorways. Loading time per passenger per channel also quickens by virtue of having no steps. As conductors cannot observe all doors directly, they must now be extra careful to ensure that the doors are clear before moving off. In order to take advantage of the vehicle's larger capacity, the scheduled headway is increased from every 2 minutes to every 3 minutes and 23 seconds. In this scenario, the minor stops with relatively low passenger demand are eliminated. Candidate stops for elimination are those at which boarding and alighting demand is less than the through volume. As a policy, stops were not eliminated if they served as a transfer point, or if the distance between adjacent stops would exceed 600 meters. It was assumed that all passengers formerly served by minor stops were redistributed to the other major stops in such a way to minimize their new total travel time. This is the equation we use to calculate the passenger demands at the remaining stops. In this scenario, streetcars would no longer be required to come to a full stop before every face-pointing switch. It was assumed that any new technology for special track work and switches would allow for streetcars to proceed safely at full speed. The above measures were studied separately and in combinations in order to examine possible interactions between measures. A total of 20 different scenarios were simulated, but we will discuss the most important findings. To account for the effect of traffic signals, traffic, passengers, and other non-idealized conditions, traffic microsimulation was necessary. PTV's Vissim microsimulation package was used. Each scenario was simulated 10 times using different random seeds. For each run, vehicle record files were generated that contain each vehicle's location, actual speed, desired speed, acceleration, and reason for delay. An average of the cycle time, as well as a standard deviation, is calculated and used to compare the effectiveness between different scenarios. To assess how various sources of delay are impacted, the lost time was calculated for every half a second and aggregated over the study period for each source of delay. The simulation results and analysis were performed at the University of Toronto and Ryerson University's respective transportation labs. Matthew Harvey, a Transportation Engineering Masters of Applied Science candidate at Ryerson University and co-researcher for this project, explains the findings.
Overall, the use of new vehicles reduces time loss under all scenarios. The time savings for all of these cases are statistically significant. For red light delays, the change didn't seem to depend just on the use of low-floor LRVs, but it also changed according to what other measures were being implemented with it. Overall, there is no clear pattern, and the change of red light delays is minor. However, we did notice that red light delays tend to increase if the red light delays in the before case were already fairly small. The queues at King and Charlotte Street practically vanish using new low-floor LRVs. This happens for 3 reasons. Firstly, the frequency of transit units is reduced, which reduces the arrival rate at the queuing system at King and Charlotte Streets. Secondly, the reduction in frequency also reduces the amount of time for which a center lane on King Street, westbound towards Spadina, is blocked by a right-turning streetcar, which can often wait an entire green cycle just to execute a right turn. This reduction in frequency of right-turning streetcars can therefore improve westbound traffic flow on King Street and improving the service rate at the King and Charlotte queuing system. Finally, the all-door loading regime with the new low-floor LRVs dramatically reduces the dwell time at King Street northbound stop, which decreases the likelihood of a backlog of right-turning streetcars on King Street. For the same reasons, time lost in mixed traffic also decreases for all comparisons. Despite this reduction, though, time lost due to traffic still remains a problem, as the new streetcars experience the same lack of priority at intersections. Not surprisingly, the time lost due to passenger stops decreases with the use of new low-floor streetcars. As we'll see later, much of the time savings occurred at the King Street northbound stop. Bunching decreases with new vehicles, likely because of the increase in scheduled headway. We should mention that as the current fleet of CLRVs is coming to the end of its lifespan, it's fairly certain that the TTC will replace it with an entire fleet of low-floor LRVs. Given that the time savings is significant for all scenarios using low-floor LRVs at the reduced frequencies, we recommend that this measure be implemented. The time savings with all-door loading for CLRVs are statistically significant. Bunching decreases with this measure. It's fairly commonly known among transit service planners that overall higher operating speeds can improve reliability with all else being equal. Red light delays generally improve, but the time savings are minor. Although time-saving servicing stops may increase the likelihood of the streetcar arriving at a green light at the next intersection, this improvement is limited if the time savings weren't large enough to avoid the next red light. In this later case, the time savings realized from servicing passenger stops would simply be reclassified as time waiting at red lights, as such streetcars would simply arrive earlier at the red lights. This was observed for the comparison for which only all-door loading was used compared with the base case. In other comparisons, implementing other measures would result in enough time savings for the streetcars to start avoiding the red lights. As expected, the time lost servicing passenger stops decreased using all-door loading. Surprisingly, our results show that the reduction in time loss due to passenger boarding and alightings is actually quite small, usually below 1 minute. When we examine the dwell time savings by each individual stop, we see that the time savings is greatest at the King Street northbound stop, which has a boarding demand of over 1,000 passengers per hour and a alighting demand close to 0. At the other stops, the boarding and alighting demands are more equal, which reduces the effectiveness of all-door loading. Under the single-door loading scenario, passengers must line up in a single channel to board. With all-door loading, that means there are an additional 2 boarding channels, resulting in the time savings that were greatest at the King Street stop. Using all-door loading with the CLRVs also tends to decrease queuing time at King and Charlotte Street substantially. It was surprising to see that the all-door loading measure had an even greater effect on queuing time than it did on the actual passenger service time. We saw that the move to all-door loading resulted in substantial reductions in the amount of time for which streetcars are stopped to load passengers at King Street. Since the King Street northbound stop is at the end of the queuing system, any reduction in dwell times at King Street also allows northbound streetcars to clear the stop faster, reducing the likelihood of a backlog of right-turning streetcars onto Spadina, and thereby improving the rate of service at the queuing system. We verified this service rate was indeed faster when all-door loading was used. However, even with all-door loading, streetcars still lose 7 minutes in the queuing system. For the same reasons, time lost due to mixed traffic also decreases under all comparisons. Given that the time savings is significant for all scenarios with all-door loading, we also recommend that this measure be implemented on the remaining CLRVs that have not been yet replaced by new low-floor LRVs, and that all-door loading certainly be implemented for stops with high boarding to alighting demand, such as King Street northbound. The time savings with the repeal of the stop and proceed policy are generally statistically significant, with the exception of the base case comparison. Aside from not having to slow down on the approach to each intersection, the repeal of the stop and proceed policy resulted in further secondary time savings from other sources. The red light delays consistently improve, as we expected. This was probably because the streetcars were more likely to avoid the next red light by not having to slow down on the approach to intersections. It's also interesting to note that the red light time savings is greater for CLRVs than for low-floor LRVs, possibly due to the effect of passenger service time savings being replaced by waiting at red lights, when the low-floor LRVs arrive at the red lights earlier. Bunching generally improves, again as we expected, for the same reasons that faster service is generally more reliable. Given that the time savings is significant for most of the scenarios with the repeal of the stop and proceed policy, we recommend that this measure be implemented, provided that whatever new technology is adopted for special track work and switches can safely handle streetcars at full speed operation. The changes in cycle time because of stop elimination are generally not statistically significant. In fact, the implementation of stop elimination results were only significant with the conditions involving new vehicles or the repeal of the stop and proceed policy. Red light delay increases with all scenarios in this measure. This was likely because the streetcars were held at red lights where the stops were removed. As we have seen with the other measures, if the time savings for one source of delay aren't enough to allow the streetcars to beat a red light on one cycle, the time savings from the source are simply replaced by time losses at red lights by the streetcar's early arrival at the red lights. Time spent servicing stops decreases by around 3 minutes. We assume that riders would not switch to another mode as a result of any changes to the service. Now, simply because there are fewer stops, the streetcar wastes less time physically opening and closing the doors, as well as slowing down for and accelerating from stops. Queuing time either did not improve and sometimes increased when CLRVs were used. As the queuing system can depend heavily on the passenger demand at King and Spadina, it's not surprising that the removal of stops made the queue worse, given that King and Spadina remains. At Richmond Street, the next stop, around 22% of the passengers would choose to backtrack and board at King Street, and exacerbate the excessive dwell times at this stop. This then increases the duration for which the center lane on King Street westbound is blocked by a turning streetcar. This in turn worsens the traffic flow on King Street, thereby reducing the service rate at the queuing system at King and Charlotte Streets. However, when the new low-floor LRVs are used, queuing is reduced despite the increase in boarding passengers at the King Street stop. This is probably because, although the number of passengers increases, the total dwell time is reduced since there are now many boarding channels available with the new low-floor LRVs. As a result, a backlog of streetcars along King Street West becomes much less likely. For the same reasons, time lost in mixed traffic generally worsens as queue time increases. One issue is that our simulation can't capture the relative value of in-vehicle versus out-of-vehicle travel time. Since the Spadina Streetcar line passes through shopping districts, many passengers carry heavy grocery bags. So it's possible that these passengers would value short access and egress times over faster operating in-vehicle speed. Overall, the time savings were generally not statistically significant, and sometimes worsened with CLRVs. Stop elimination is better with low-floor LRVs and actually reduces the total lost time. But because many passengers may be sensitive to the out-of-vehicle travel time, we can't recommend stop elimination to the Spadina streetcar without more study.
As we saw just now, each of the measures we looked at had varying effects on delay time. Low-floor LRVs at reduced frequency alone results in a 40% reduction in round-trip time. Firstly, the delay due to queuing, the largest source of delay, practically vanishes both because of the reduced arrival rate of the queuing system, as well as the improved westbound traffic flow on King Street West. Time lost due to passenger loading and bunching also decreases. However, the change in red lights was not consistent. All-door loading on CLRVs at the original frequency alone results in an 18% reduction in round-trip time. Once again, the delay due to queuing decreased drastically, but did not vanish altogether. Delays due to passenger loading, bunching, and mixed traffic also decreased. Once again, the decrease in red light delays was not consistent. The repeal of the stop and proceed policy at face pointing switches alone results in a 16% reduction in round-trip time. The biggest reduction in delay was the red lights. Other sources of delay, such as bunching, were also reduced to varying degrees. When minor stops are eliminated, the round-trip time actually increases by about 1.9% for several reasons. Firstly, some boarding passengers were redirected to the very heavily used King Street northbound stop, increasing the dwell time of streetcars there. This then worsens the queue upstream at King and Charlotte Streets. Once again, our study is valid only for the spring of 2014, during which all streetcars would short-turn at King Street West. Nevertheless, we would like to make the following recommendations in light of these findings. That higher capacity low-floor LRVs with all-door loading be deployed at reduced frequency of 3 minutes and 23 seconds. That all-door loading be implemented on any CLRVs that remain, especially at stops with high boarding demand, such as the King Street northbound stop. And finally, that the track switching technology be upgraded to allow for streetcars to operate safely through face-pointing switches at full speed. Together, these measures would result in a capacity increase of 4% and a reduction in round-trip time of 48%, decreasing the round-trip time from 45 minutes to just 23 minutes. Substantially fewer vehicles would be required to operate the line, reducing the operating costs, and allowing the TTC even more flexibility to improve service throughout the system. As we come to the end of our first installment in this two-part series, we'd like to reiterate the most interesting patterns that became apparent during this simulation. The queuing system at King and Charlotte Streets accounted for the largest source of lost time. As explained earlier, both the arrival rate and the service rate of the queuing system were improved with lower service frequency. The service rate was further improved by the decrease in dwell time at the King Street northbound stop. Perhaps the important takeaway is that whilst it is often said that frequency equals freedom, excessive frequency beyond what the system can handle is not. A scenario with new low-floor LRVs at the original frequency of every 2 minutes was also simulated, which resulted in much longer queues. This is an extreme example in which it would be unwise to demand that frequency be maintained with the new low-floor LRVs. The other important finding was that none of the measures considered so far were able to eliminate red light delays entirely. Some scenarios that resulted in time savings in other sources of delay would result in those time savings being replaced by additional red light delays if the time savings were too small. In part 2 of this series, we'll examine the effectiveness of 2 additional measures at further reducing red light delays: nearsighted stops and transit signal priority for the remaining major intersections. Thanks for watching part 1 of our analysis of the Spadina Streetcar.